So we were on sorting algorithm. Yeah. So we have just seen the insertion sort and merge sort. So these are the respective efficiencies. Now consider, so whenever we talk about the efficiency and when we want to compare two algorithms, like when we are really interested in time. See, guys, I must have told you about this in the previous semesters about the time required for running an algorithm or running the code. So we always want our code to be run faster, right? A faster code will give you output in a faster way, right? But whenever we compare, see, when we are comparing distances or weight or anything, that has to be in the same unit, right? You cannot compare a feet with inches with centimeters and meters, right? It has to be converted into one particular measure for comparison. So same way, when we are comparing the runtime or we are comparing the algorithms, how if we are comparing an algorithm run on a faster computer or run on a slower computer, so it will not actually give us the exact measure, right? So we have to keep the same basis for comparison of the code and algorithms. So we know that if the computer is faster and running an insertion sort and a slower computer running merge sort, both must sort an array of 1 million numbers. Consider this. Okay. So suppose computer A execute 1 million instructions per second and computer B execute 10 million instructions 10 to 7 per second. So computer A is 100 times faster than computer B, right? So a computer which is faster or a computer which is slower, and if we run a code on that, so definitely your code or the runtime will be dependent on how fast your computer is, right? So we need to have a common measure, we need to have one basis on which we can compare the codes and algorithms. Now consider computer A takes, to sort 1 million numbers, computer A takes this much seconds, 2000 seconds, okay? And B takes 100 seconds. So by using algorithm, worse running time grows more slowly. Computer B runs 20 times faster than computer A. So for 10 million numbers, insertion sort will take 2.3 days and merge sort will take 20 minutes. Okay, so this is how, but here we are considering the runtime and the computer time, right? Pseudocode conversions. So algorithms are typically written in pseudocode. A pseudocode is something which is, algorithmic fashion or which is somehow related or similar looking like C and C++ or maybe looking like Java. So that's the pseudocode. But pseudocode is not the actual code, right? Because when we are writing a pseudocode, we are not actually concerned about the software engineering or data abstraction or error handling or certain kind of things. So we just look at the logic and we look at how the arrangements of the steps are done in the pseudocode. So pseudocode is not a code which is accurate and exact and error free which can be run, but which is little somehow algorithms and looking like C++. So sometimes we may use assignment statements like this instead of writing this equal. So this would be the assignment statements. So in the conventions, local to the given procedures, we shall not use the global variables without explicit indication. So generally we would be using the local variables. Array elements, array we may use. Particular attributes is assessed using the attributes name followed by the naming the object with the square bracket. So object we can use with the square brackets. You know these conventions, so we are going fast track. So particularly your pseudocode will look like this. So your merge algorithm or a merge pseudocode will look like this. Okay. Yeah, growth of functions. Now we'll see another topic, which is a growth of functions. Just now we had a discussion on how to measure algorithms, how to algorithm. So let's have a look at this. So we can time how long it takes a computer. So how to decide how long it takes a computer. So what if the computer is doing other things? So this is a concern. So if you have given a multiple tasks to a computer and then you are measuring the performance of a computer, then it may not be the right thing if it is doing multiple things. So because your processor would be busy in doing other executing other processes, and that's why you may not find out the exact time taken by the computer. And what happens if you get a faster computer? So computer to computer speed varies, right? So if this is there, so it's not good idea to look at the time taken by a computer. We can measure how many machine instructions an algorithm takes. So different CPUs will require different amount of machine instructions for the same algorithm. You all know whenever we write a high level code, so one particular code would be converted into the machine level language, right? It's machine language. So whatever is the manufacturer codes and instruction set is given for that machine, it will be converted into that. So it's possible that one manufacturer will convert one line into multiple instructions, or it may be a different setup for different machines. Compare as it is machine dependent, or it is dependent on a particular brand or make. So how to compare the algorithm? So we can loosely define a step as a single computer operation. Okay, so one step we will consider as a one unit or one thing, and that's how we are going to consider now. So for example, a comparison would be one unit, an assignment would be one unit. Now here we are not considering, because as I mentioned, feet cannot be compared with inches. It has to be brought onto the same level. Either feet has to be converted into inches, or inches have to be converted into feet, whatever. And then you can compare the things, right? So same way to compare the algorithms, to identify, or whenever we want to make a comment on its efficiency, it has to be on the similar ground. So we need not look at which computer is it is running, We are not considering the time taken by the computer or how a machine converts into the machine instructions. But we will consider the algorithm itself. So look at the algorithm, look at the steps of the algorithm. In every step, there would be a small unit. It may be a comparison, it may be an assignment, it can be a multiplication operation assigned to a variable, it can be small units. So look at the granular level of the instructions written in the algorithms. And that's how we can call it as a step or a unit. So regardless of how many machine instructions it translates into, so this allows us to put algorithms into broad categories of efficientness. Okay, so this is how we are going to consider in the entire course. So an efficient algorithm on a slow computer will always beat an inefficient algorithm on the fast computer. This is what we have already seen in the example. Okay, so you may write an efficient algorithm but run on a slow computer, it will be slow. But inefficient algorithm on a faster computer will give you good results. So that's why we will consider the steps in the algorithm. Now look at this bubble sort running time. So bubble sort running time, it has these many steps. N square minus n divided by 2 steps. Let's say the bubble sort takes the following number of steps in the specific CPUs. So in Pentium, 58 multiplied by its steps. In Motorola, maybe 84 multiplied by this. In Pentium, it may be 44 multiplied by this. Okay, but look at this, it has all n square common, right? As n increases, the other terms will drop out because these are the constants. 58 is a constant, 84 is a constant, 44 is a constant. So whatever is the computer type, whatever is your machine, if this is your bubble sort, and whenever your n increases very highly, like when it increases from tens to hundreds to thousands to maybe millions, then these numbers, which are constant numbers, will drop out, and strictly your runtime will be dependent on the n square. Okay, so later it will be something, 29 n square, this is 42 n square, this is 22 n square and all. So as processors change, the constants will always change, right? But this exponent on n will not change because that's the bubble sort algorithm. That's the logic for the bubble sort. So this exponent on n will not change. It will be always n square. But this is how we have written the bubble sort. Thus, we can't care about the constant. So that's why we will not look at the constants, but we will look at this number n and the values or the exponents of n, right? Now these inequalities and all those things I'll just leave. I hope you have learned these searches and sortings in data structure. Guys, you know the searching algorithms. Consider a linear search algorithm. So linear search algorithms will take n steps, and binary search algorithm will take log n steps. Okay. And if you look at number n and log n, so definitely a binary search is a faster algorithm if we compare with the linear search, right? Same way, so look at the sorting algorithms. Bubble sort, n square steps. Insertion sort, n square step. So there are other more efficient sorting algorithms also. So if we look at this in principle, looking at the other constants and other steps, Which is the fastest algorithm? Heap sort, quick sort, and merge sort. These are the fastest sorting algorithms. We will do analysis later on. So quick sort is fastest. Sometimes it is not guaranteed. So big O notation. We call that as a big O notation, order n square. So what we were talking in the previous slide, that whatever is the machine, but when we run a bubble sort, there is a term n square, n square, n square everywhere, right? And that's how it is dependent on n square, or it is dependent on n to the power 2. And this is called the big O notation. In big O notation, we define the complexity or efficiency of the algorithm. We read it as a big O order n square. This means that input size increases, the running time of the bubble sort will increase proportional to the square of the input size. So whatever is your input size, which is n, your runtime is proportional to the square of the input size. And your sequential search or a linear search would be always order n. So big O notation n, or we call it as a order n. Your sorting algorithms would be order n square. These proofs and all we'll see later. What I want to show you here is the, look at this. This is your x square. So your x square performs like this on the graph. This is x square. This is x square plus 2x plus 1. This is x square plus 2x plus 1. 4x square. Sorry, this was nothing. These are the three functions. Look this, how this function performs. See, this function performs like this. And this function performs like this. Okay. On units, number of input, which is better? And if you increase the numbers, see which arc looks better. So this is how it x square works. So consider these functions, the performance of function when x increases or when n increases your input size. Now look at this. Function growth rates. See, order 1, order log n, order n. This is n log n. This is n square, n cube. This is how it grows. If the input size is 1000. If your input size is 1000, means you are sorting 1000 elements, or if you are searching 1000 elements, order 1 is a constant. Order 1 will be always 1. Order n will be always n. See, order log n will be 10. Order n will be 10 cube, means 1000. So order n will be 1000 for 1000 numbers. Order n log n, these many steps your algorithm will take for 1000 input size, right? So if you are doing a searching or a sorting or a matrix multiplication or whatever, whenever we say order n square, so order n square, and if your n is 1000, your algorithm will run, or it will have 10 raised to 6 steps to execute. Okay, so 10 raised to 6 steps, when it executes, definitely it will take a longer time than any algorithm which has n log n order, or maybe just a log n, or maybe just n. So if this increases, if we move from this order to this order, look at how your number of steps are increasing. So some algorithm, consider an algorithm which has a big notation order n cube. N cube are generally, matrix multiplication kind of a thing, where you have 3 loops for I is equal to 1 to n, j is equal to 1 to n, and k is equal to 1 to n. So these 3 loops are running, one to another. Consider your code. You are writing here a loop from 1 to n, and you have a nested loop, again 1 to n. Again, you have a nested loop 1 to n. So you are running one, and here you have written some statements in the code. So let's say algorithm pseudocode or whatever, and you have here some number of statements. So how many times this entire code, these four statements would be run n times, multiply by n times, and multiply by n times, making your algorithm n cube. Okay, so depending on the n. So if n is 1000 or n is 10 or n is 100, whatever, but these 4 steps would be run n cube times. So making your total, these 4 steps multiply by n cube. So these many steps it would be. And definitely it will take longer time. And we call that particular code ka efficiency as n cube, right? Now, whenever your algorithm is order n raised to 4, rate is 10 raised to 12. Order n raised to c is 10 raised to 3 multiplied by c. And when you have 2 raised to n, it will be 10 raised to 3, 0, 1. These many steps it will be converted to, and your code will run for these many times. When it is n factorial and your n is 1000, look at how big the number is. So your one step would be run for these many number of times, resulting a very high growth rate in your function. So if your function behaves like this, and when you move from this order to this order, definitely your programs will have this kind of efficiency, and your programs will run for these number of times, resulting a very increase, a very high increase in number of steps at the time of execution. So many interesting problems actually lie in this category. So whatever problems we are going to see now, so they would be in our syllabus. We are going to target our problems on this basically, because these problems would be solved in less number of iterations or less number of time. So major focus of our syllabus is considering those problems whose order or whose big notation or whose function growth rate is n square, n cube, or 2 raised to n, or n raised to n. Now we have seen these numbers. Okay, these numbers. If we plot the graphs for these numbers, see, this is a logarithmic scale. Look at those functions. So this is order 1. So order 1 is a just constant, right? So whatever is your input size is 2, 3, 4, 5, 6, whatever. This is straight because this is order 1. This is how your order n looks. So this particular function behaves like this. So your increase in the input will slightly increase this. Now look at this. This was log n. This is n. N behaves like this. N log n is like this. This is n square, 2 raised to n, and n factorial. See, now if the input increases, okay, if the input increases, how this behaves? Like we have seen the curve for corona, right? So corona increases exponentially because its growth rate, the function is exponential function, and that's why the exponential functions behave, they change their growth depending on the increased size of input. अगर number of input बहुत ज़्यादा बढ़ता है तो this will be very high, and this is how it behaves. So same way. Yeah. So what have we seen today? We have seen the components of algorithms. We have seen the different functions and how do these functions behave based on increasing size of input. Okay. What we have understood today is how to compare the algorithms, right? So whenever we compare the algorithms, we are not going to compare the algorithms based on how they are run, on what machine they are run, but we will see the algorithm or a pseudocode and total number of instructions. So how many steps the algorithm will take for completing its execution. This would be our major focus. Now, whenever we are looking at the problem, so today we have just compared some sorting and searching algorithms. So based on their efficiency, we can identify which algorithm performs in a better way when the input size is say n is equal to 10 or 100 or 1000 or a million. And based on that, we can compare these algorithms, and for a situation we should be in the position to compare the algorithm. Agar hame for example, for a particular application we consider 10,000 of input size, right? So we know for this particular application we have input size 10,000, and we want to have a searching algorithm, or we want to have a sorting algorithm for the input size n is equal to 10,000. Which algorithm would be better? Which sorting algorithm would be better based on their efficiency? And we can compare that, and we can recommend a good algorithm or a better algorithm out of those algorithms, and we can सजेस्ट और रेकमेंड कि इस सिचुएशन में इतना इनपुट अगर लगता है तो ये एल्गोरिदम बेटर परफॉर्म करेगा, एंड लेट्स अडॉप्ट दिस पर्टिकुलर सॉर्टिंग एल्गोरिदम for this particular application. So that's how we can do the analysis of the algorithms. So looking at the situation, looking at the demands of the problem, looking at how much is the input size, we can identify the working of the algorithms, we can calculate the efficiency and compare, analyze, and recommend a better solution. So everybody understood whatever we discussed today, guys?
Yes, ma'am.
Yeah, Ayush, Anurag, Jay. So this is how this course is. We would be looking at, yeah, okay, Ninad, Nikhil. Swishti. Okay, good, good. Tomorrow onwards, we will be looking at a particular problem. We will be looking at a particular technique, and how do we attempt to solve a particular problem or situation using different techniques, and we will compare which technique would be better for this particular solution. Okay. So that's it for today. Any doubt so far? Any doubt? Thank you, guys. Okay. Yeah, thank you.